Sure, think of big cities. Okay, let's go through it then, here. All right. What is an urban heat island? Okay, I'm giving you a picture here of Denver, Colorado. And this is just a general definition of what an urban heat island is. Okay, it's a town, city with a lot of built-up, hardened structures. What do I mean by hardened? Concrete, asphalt. Okay, removal of natural vegetation. Now, you guys, a couple of weeks ago, took infrared ground temperatures around the campus here. And what do you remember about the ground temperature between the vegetated surface and the other two, just generally in terms of temperature? Yeah.
Vegetation.
It's way lower. Remember that? You guys were getting temperatures in the 50s at the ground, and you're getting temperatures in the 70s and 80s on the concrete and the asphalt surface. Remember how the atmosphere heats up? Heats from the ground up. The atmosphere gets heated by the ground. So the warmer the ground is, the warmer the air above it should be, unless you get a big wind blowing, which we saw that too. So look what we do in our cities. We remove a lot of the surface vegetation and we replace it with surfaces like you took the temperature on recently. Asphalt, concrete, things like that. So the theory behind an urban heat island effect is that we're heating the surface up. If we heat the surface up, we're going to heat the air up. So that's the idea behind it. So if we were, this is again theoretical, if we took a temperature profile across an urban center, this is the kind of thing we tend to see. Now this is air temperature. You go out where there's a lot of vegetation on the outside of the city, a rural area, and you're going to get a relatively low temperature. In this case, we're looking at 85 degrees. As we move closer and closer into the center of the city, we end up at 92. Now this is just theoretical. I mean, this is just one kind of an example. And then as we move out to the other end, suburban residential, an area where there's more vegetation, the air temperature lowers again. So this is the idea of the urban heat island, that city cores are warmer than their surrounding areas because of what we've done to the surface. Okay? Now here are two photographs in Baton Rouge, Louisiana. And one is just a standard aerial photograph, same area with an infrared photograph, kind of gun that you used outside. Infrared photography takes a look at the temperature of the surface. So if we take a look over here, what this is showing here is that your red colors are higher temperatures, your green are the cooler temperatures, and yellow is in between. So if we take a look at what do these red areas correspond to in Baton Rouge, they correspond to hardened surfaces, concrete and asphalt. Look how much they're heating up. Now again, you guys did this yourself. You saw for yourself the readings around the campus. But this is a kind of a massive area, a lot bigger than Yavapai College campus. So there you go. I mean, this is the basic reason behind the urban heat island effect. This is why city cores are warmer than outlying areas. Because look at the temperature. Green, cooler temperatures corresponds to these trees or vegetation. Red, where we removed it, put in hardened surfaces. The blue is very cool. That's water. Okay, causes of urban heat islands, well, like we said, the surfaces, and surfaces like asphalt and concrete, and that results in a number of things, all right? Remember, we just looked at albedos, so if you can imagine a dark surface like this, much lower albedo than a vegetated surface, meaning it's going to reflect very little solar radiation, it's going to absorb a lot of solar radiation, okay? So lower albedos. One issue. The greater conduction of heat energy, and this is just what you talked about really, where this solid surface is able to conduct and store a lot of this heat just under the surface, where it can't on a vegetated surface. It doesn't conduct heat, it's more of an insulation with a lot of air around the vegetation. A solid surface conducts and holds a lot of that heat, and then when the sun sets at night, it releases it. So greater conduction of heat energy. Drier surfaces. Okay, now this is an interesting one. Think about summer in Prescott, and a little thunderstorm rolls through. All right. It dries out pretty quick around here in the summer, I've noticed, when it's hot. What kinds of surfaces dry out more quickly? Like, let's say you're on your street, you live on a street somewhere, and you've got some grass or vegetation in your yard. What dries out more quickly, the road or your grass? The road dries out way more quickly. So, and here's what happens is, shortwave solar radiation, when it strikes a surface, if there's any liquid water on the surface, it will work to evaporate that liquid before it starts heating the surface up. So that heat energy goes first into taking liquid water molecules that are very close together and causing them to evaporate. That takes a great deal of energy. So the sun's energy first goes into evaporating the liquid. So the longer your surface is moist or wet, the longer it's not going to start warming up. But if your surface dries out quickly, it's then going to start warming up more quickly. So that just the fact that these surfaces dry out more quickly means they're going to warm up more. And finally, this higher net radiation. I showed you the map at the beginning of the lecture. We looked at the globe. We looked at where all that heat energy in terms of watts per meter squared was the greatest. Okay, these are these surfaces without vegetation, without a lot of cloud cover. Anyway, it works that way as well with these hardened surfaces. They absorb more overall net radiation, so they're going to get hotter. Okay, another cause of urban heat islands, and I'm going to give you the example of Vancouver, British Columbia, because I'm familiar with it. This is downtown Vancouver, just to set it up. You're looking out to the ocean here, and generally the wind is blowing off the ocean from a westerly direction into the city of Vancouver. Let's take a look what happens here. The irregular shapes of buildings. Okay, what about the irregular shapes of buildings? Produces something we call radiation canyons, all right? And I'm going to go over to the board here and do a little diagram. Now, Vancouver's not unique in this. I'm just using it as an example. So we have a lot of buildings, a lot of tall buildings, and they're irregular shapes. So let's just take a look at one example. So we got the sun up here. We have short-wave solar radiation coming down. What happens when it strikes the side of this building? What happens to the shortwave? Okay, some's absorbed and some's reflected. Okay, let's take a look at the reflected bit. So we're going to go down here. Then what happens over here? Reflected again. So this would all be the short wave. But remember, in addition to short wave solar radiation coming into these buildings here, they're going to be absorbing it, and they're going to be giving off long wave radiation in all directions. Long wave across from this building to this one, and then same like this. So one of the ways you can think about this is that these tall buildings trap short wave and long wave radiation. So they're holding it in. So that's another way that these urban centers trap heat and heat up more. All right. Now another effect that these tall buildings have, and I think it's probably pretty clear when you look at this photograph here, if you've got wind coming off the ocean here, these buildings create a lot of friction and drag on the wind, slow it down. Now, again, you observe for yourself outside what happens when you get a stronger wind blowing across a surface in terms of its temperature. It will cool it down. But we are reducing the wind speed here. If we reduce the wind speed, we're going to keep the temperature up. So a couple things then. Irregular shapes of building basically trap short wave and long wave radiation, cause it to heat up, and they lower the wind speeds because of friction and drag on the wind, and that's going to keep the temperature up. Okay, here's another cause, urban heat island effect. Now you're looking at a picture of Los Angeles on a nice clear day. Air pollution is what you're looking at, okay? Now what is air pollution? Aerosols. You recall the term aerosol. Solid bits of anything floating in the atmosphere that are buoyant or floating, okay? This stuff, okay? What do you think most of this stuff is in terms of it? This is an aerosol. What do you think the source of these aerosols in LA are? mostly from automobiles, internal combustion engines that release solid bits of carbon out the tailpipe, all right? So that's one of the issues there. Now, what can happen then is that, again, let's go to the board. So we're a surface here in a city. And, you know, we've got these little bits of carbon up here, all right? Long wave radiation is always being released from Earth's surface. What happens when long wave radiation hits these solid bits of material? What do the bits of material do with the long wave? They absorb it, okay? They're absorbing it and they are re-radiating it in all directions that the atmosphere can absorb. Remember, our atmosphere is really good at absorbing long wave, but not good at absorbing short wave. So these little bits of carbon that we see floating around in LA here are absorbing long wave and re-radiating out to the atmosphere and heating it up, okay? But it's not really quite as simple as that, because we've talked about this before too. Aerosols, or particulate matter, don't just absorb long wave radiation from our surface. They can reflect short wave solar radiation. So incoming short wave solar radiation, particularly if they're light colored particulate matter, incoming short wave can get reflected back. What's that effect on the temperature? Yeah, so, you know, it's interesting. You got a couple of different things that work here. You know, we're at the same time reflecting short wave, we're absorbing long wave. But we think the overall effect of this, we think this has a bigger effect. So we think that particulate matter works to, we think, warm the atmosphere up. But remember, short wave is also being reflected. Now, here's something else that's we've discovered relatively recently that's pretty interesting, is that it turns out for clouds to develop and then for precipitation to fall out of those clouds, we need something called condensation nuclei. All that is are aerosols, solid bits up there. Turns out that we need a solid bit of material floating around in the atmosphere in order for H2O gas molecules to condense into liquid on that particle. And then in clouds, we also need particulate matter for those cloud droplets to attract to, get big enough to overcome the buoyancy of the atmosphere and fall out of the cloud. Turns out these are absolutely essential to get precipitation processes going. So, if we put a lot of particulate matter up into these areas, what effect is that going to have, do you suppose, on the amount of precipitation we get? It's going to increase. And we found that we've looked at areas downwind of large urban centers that put out a lot of air pollution. We've seen an increase in precipitation.